And welcome back, students, to our next lesson on hardware. We're going to discuss today non-volatile memory. So let's get started here. Non-volatile memory, or non-volatile storage as it's sometimes called, is a type of computer memory that can retrieve stored information even after shutting off the power. Compare this to volatile memory such as RAM, which loses its data upon power loss. In this lesson, we're briefly going to cover many different forms of non-volatile memory. So let's first discuss the role of non-volatile storage. So non-volatile memory is typically used to the task of long-term persistent storage. This is typically, it provides a lower performance or has a worse write endurance than a volatile memory. So that is one downside. So its role is it's going to do long-term storage. At the trade-off, it's going to have a worse performance. Now let's start talking about disk storage. A general category of storage mechanisms where data is recorded by various electronic, magnetic, optical, or mechanical changes to a surface layer of one or more rotating disks. This is when you start thinking of things like your hard drives, DVDs, Blu-rays. That's all form of disk storage. Now, a disk drive is a device implementing such a storage mechanism. So whether it's your hard disk drive, or it's an optical drive, or some other kind of mechanism that is going to be able to read whatever that disk media is. Let's talk a little bit about their access methods. Well, digital disk drives are what is known as block storage devices. That means that each disk is divided into logical blocks, or a collection of sectors, that are addressed using their logical block addresses. Now, originally, the disk capacity was very low. Think about things such as floppy disks, like the original. I'm not talking the 5-inch floppies, but let's just talk about the 3-inch floppies for a second. The 3.5-inch floppy had about 1.5 megabytes of storage. Just think about that. 1.5 megabytes. It's a couple Word documents and you're done, you know. Whereas today you look at a flash drive, you can pick up a flash drive and it's got like 16 gigs. Quite a significant difference. All right, now obviously this has been improved in several ways. The improvements in things like mechanical design and manufacture allowed smaller and more precise heads for reading, which means that more tracks could be stored on each of the disks. So because the heads are small, the tracks could be, finer. And the advancements in data compression methods permitted more information to be stored on each of the individual sectors. All right, since we're talking about mechanical stuff, let's talk about rotation. Mechanically, there are two different motions occurring inside the drive. You have the rotation of the disk inside the device and the side-to-side motion of the head across the disk as it moves between the tracks. And there are two types of disk rotation methods. There's what's known as constant linear velocity, which varies the rotational speed of the optical disc depending upon the position of the head. And then you have constant angular velocity, which spins the media at one constant speed regardless of where the head is positioned. Now, some basic terminology, just to kind of familiarize with you, because with mechanical stuff, there's a lot of stuff to really kind of know, versus disk. This generally refers to magnetic media devices. So that's like your Blu-ray disc, your hard disk. It's just the individual disk right there. Now, if you see DISC disk, this is typically done when it's required for trademarks for certain optical media devices. Now, you can use disk with a K and disk with a C kind of interchangeably, but disk with a C is more often referred to like optical media. Like you're never going to have a hard drive disk with a C. It's always disk with a K. The platter is an individual recording disk, so a hard disk drive contains a set of platters. You also have these in things like your optical drives. The developments in optical technology have led to multiple recording layers on DVDs, for example. That's why you'll hear about multi-layer DVDs. Because a typical DVD has about 4 gigs, but you can do multi-layer and boom it up to like 16 gigs. A spindle, which is simply the spinning axle on which the platters are mounted. Rotation, that's where the platters rotate. The two techniques that we already talked about that are common, constant angular velocity and constant linear velocity. We have the track, which is the circle of recorded data on a single recording surface of the platter. If you ever have burned a CD or DVD on your own, you flip it over and you can see the difference there between where the information was and where the information is not. You can see there's a distinct area. That is the track. That's the recorded data that's on your disk. Continuing on with a little bit more basic terminology. a sector, which is simply just a segment of a track. You also have load-level formatting, which is simply what establishes the tracks and the sectors on your disk. You have the head, which is the device that reads and writes information, whether it's magnetic information, such as on your hard disk, or optical, such as on your CD or DVD or Blu-ray, on the disk surface. You have the arm, which is the mechanical assembly that moves the head in and out, so whether that's a physical mechanical head or that's using like a laser. You have seek time, which is the time that's needed to move the head to a new position or a specific track on that disk. You also have rotational latency, which is the average time once the arm is on the right track before a head is over the desired sector. And lastly, we have data transfer rate. This is the rate at which user data bits are transferred either from or to the media. Now, technically, this could be more accurately entitled the gross data rate because it's before you account for like any of the speeds for connections and stuff like that, or read-write speeds between the hardware, blah blah. It's pretty much the raw speed. Now, we also need to talk real quickly about flash memory. Now, flash memory is an electronic, non-volatile storage medium that can be electrically erased and reprogrammed. There are two main types of flash memory, which are named after the NAND and NOR gates. So there's a NAND flash and there's a NOR flash. Now, NAND type flash memory can be written and read in blocks or pages, which are generally much smaller than the entire device. Comparatively, NOR type flash allows a single machine word or a byte to be written to be an erased location or read independently. A couple quick limitations of flash memory before we dive in too far. One limitation of flash memory is that although it can be read or programmed a byte or word at a time in a random access fashion, it can only be erased only a block at a time. So there is some limitation there. Another limitation is that flash memory has a finite number of program erase cycles. Right, that's pretty much all your read-write operations. You can only do that so many times. Most commercially available flash products are guaranteed to stand at least around 100,000 PE cycles before the wear begins to deteriorate the integrity of the device. Now, what that means is that if you're doing 100,000 of those, that's not very good, but there are devices now come out with 1,000,000 PE cycles. So that's why typically if you have, like, for example, solid state drive, you don't want to do a lot of deleting and restoring stuff like that, because it just reduces the overall life of your device. Now let's talk about transfer rates. Flash memory devices are typically much faster at reading than at writing. So they're a lot faster to read data, so that's why it's really good for things like your operating system. For example, you put your operating system on a solid state drive, for example. It's really good to be able to read that information and pull it up for you really quickly. Writing speeds are a little bit less, but they're still usually substantial. Now, performance also depends on the quality of the storage controllers, which become more critical when your devices are partially full. So an empty device is going to have great performance, but as that device starts filling up, it's going to start to bottleneck. Now, there has been some quests using flash memory as a replacement for hard drives. As I already mentioned, they're solid state, but one of the more recent applications is to have it replace hard disks. Now, the reason for this is because flash memory does not have the mechanical limitations and latencies of hard drives. So a solid-state drive is attractive when you start considering things such as speed, noise, power consumption, and reliability. Right? However, one of the biggest detractors for using flash over a traditional hard disk is that the cost per gigabyte of flash memory remains significantly higher than that of a traditional hard disk. Alright, that concludes our notes for now, folks. When we come back next time, we're going to be getting into the traditional hard drives, and then later we'll get into a solid-state drive. So until then.